So in this video, we're going to try and accomplish three things. We're going to talk about the domain of functions, compositions of functions, and inverses of functions. If the video turns out to get too long, then I'll break it up into multiple videos, but otherwise you can pause after each one, okay? So let's start with domain. So first of all, we're talking about the domain of a function, okay? And we know what a function is. Let's redefine that one more time. So if you remember, we said a function is a relation, because any relationship between x and a y value is a relation. So it's a relationship in which every input has only one output. Okay, so the domain of a function are all the possible inputs that exist in that function. So let's write that down. And then we're going to look at some particular functions. That should be the. So it consists of all possible inputs. And we're going to be concentrating mostly on domain, but there is a range, okay, and we'll talk a little bit about this. So the range of a function consists of all possible outputs. Okay, let's look at some basic graphs, many of which you're familiar with. And we'll look at the domain and the range of these graphs. And then what we'll do is we'll look at specific functions, and that's when we'll identify only the domain and not the range for now. Okay, so let's start with the graphs that we're most familiar with, right? The linear functions. So we know a horizontal line, or a line with a slope, is a linear function. A vertical line, remember, is not a function. So if we take a graph of a line, slope doesn't really matter whether it's positive or negative. This is going to be the same for every line. Okay, we'll just call this line L. Okay, so it does not matter what the line is, which is why I'm calling it L. Okay, so the domain is any x value where you're going to get an output, where if we drew a vertical line, the vertical line would hit the graph somewhere. Okay, so it only hits the graph once, but it will hit it somewhere. And we know that if we took a point at this x value over here, let's say that this were x equals 2, if we took a point here and we drew a vertical line, it does pass through the graph, right? We do have a y value. We already know it's a function, so don't worry about it whether it passes through the graph once or twice. It passes through it once. Okay, so we hit the graph at x equals 2. X equals 2 is part of the domain. If we took x equals -6, let's say, well, this is also part of the domain, because x equals -6 also passes through the graph. So what we're looking for is all of the x values where this will happen. And it turns out, like, if we went all the way over here, right, if this graph extended, which it does, we see arrows, okay? If we picked an x value over here and we drew a vertical line in the same way, will we hit this red line if we just continued it on, okay? And the answer is yes, we'll hit it somewhere up here. That's where we'll hit it. If we take an x value over here and we were to draw a vertical line, again, we would hit the line probably somewhere up here, okay? If we continued this line, then we would hit it somewhere up here at that x value. If we took an x value all the way out here, then again, we would hit the line. We would hit it somewhere down here at that x value, probably a little bit lower down, okay? Somewhere down here. And if we went off the screen, okay, to California, we would hit the line as well. It would be way up in the sky, but we would hit the line, okay? So that means that any x value will give us what we call a y value, a corresponding y value. So if this is x equals 2, this dot right here, whatever this y value is, it would be the corresponding y value, okay? The y value of this point would be the corresponding y value at x equals -6. So at any x value, we do have a corresponding y value. If that's the case, then the domain can be anything. So we say that the domain, we can put it in interval notation, is -infinity to infinity. Okay, so this is interval notation. In set notation, the way that we would write it is x such that x is an element of all real numbers. So all real numbers is all numbers. So we say this as x such that, remember that's what that line is. It's like saying x except here are the restrictions. And it turns out that there are no restrictions, okay? So x is an element of, that's what that little e means, an element of. And then that r with the double stem is the symbol that we use for all real numbers. Okay. X is an element of all real numbers. That's how we say this, okay? So that's domain. Let's look at range. So range works the same way. The only difference is that you would be drawing horizontal lines instead of vertical lines. So for example, if this is the y value -3, then we would draw a line through -3. And we would say, do we hit the line? And the answer is we do, okay? So this would be part of the range. So our y values are the range. Okay, if we took y equals 3 up here, then it would be the same thing. That would also be part of the range because we do hit the graph. Okay, so we're drawing horizontal lines instead of vertical lines. And it turns out that because of that, we could see that our range is also all real numbers. So even if we were way up here, we would hit the line eventually. It would be somewhere probably out here, but we would hit the line. And if we were all the way down here, again, we would hit the graph. It might be out here somewhere, but we would hit the graph. So the range is also all real numbers. So we would still use -infinity to infinity for the interval notation. Okay. We would have to indicate that we're talking about the range here, right? We would have to either put range like I did, or you could put y is an element of, so use this symbol, okay? Or you can use set notation. So set notation, you have to write the x in for domain, and you'll write the y in for range. So you don't have to do anything extra. The y itself indicates that we're talking about range. So this would be y such that y is an element of all real numbers. Okay, let's take another line. Let's take the horizontal line. So this is true for all diagonal lines. Any line with a slope, this is true for, except for the lines with the slope of 0. So let's take a horizontal line. And we'll say that this is y is equal to 3. Okay. So let's take a look at this. Let's start with domain. So domain, if we take an x value, let's say that this is 2, and we were to draw a vertical line, we do hit the graph. Okay, we know it's a function, but we do hit the graph. And that means that this is part of the domain. This is true of any x value, right? If we take an x value at -4, we hit the graph. So this is also part of the domain. And if we went all the way out here, again, we would hit the graph. We would hit it at y equals 3. So our domain, once again, and I'm going to put in the x is an element of this time, just so that you could see how you would write it if you didn't write the word domain. Okay, so this symbol means is an element of. You can see it up here as well. Is an element of. Okay, and in set notation, it would look just like this. You don't have to write it in both. You can choose. I don't care which one you use. Okay, what you'll find is in some of our later problems, set notation, it might actually be easier. It's up to you. Okay, let's take a look at the range. So let's take a y value. Let's take y equals -5. Well, if we draw a horizontal line through -5, we actually never hit the graph. This is not part of the range. Okay, the horizontal line never hits the graph. In fact, the only y value that's part of the range is y equals 3. This is the only case where we draw a horizontal line and we hit the graph. We hit it an infinite number of times, and that's okay to hit it an infinite number of times. Can't really see. Let me see if I could. So that's y equals 3. Nope, that still doesn't look right. Okay, we got it. Okay, that's better. So it only hits the graph at y equals 3, which means that the range here is just from 3 to 3. Okay, so how do we write that? Well, in interval notation, we're saying the y values start at 3, but they also end at 3. So y goes from 3 to 3, and 3 is included. Okay, so we use brackets. 3 is included. Starts at 3, ends at 3, but 3 is included. So we have the brackets. If you put parentheses here, then you would say nothing is in the range. You have to have the brackets, okay? If we were to write this in set notation, and this is why some people prefer set notation, we would just say y such that, so y with a condition, and the condition is y has to equal 3. Okay, so we just put our condition in there. Okay, let's take a different type of graph. Let's say that we took something quadratic. And hopefully you've all seen what a quadratic looks like. It looks like it's a parabola. And let's take a quadratic that has a vertex at the origin. And for those of you who haven't seen quadratics before, okay, these are parabolas. They keep going and they don't go straight up. This is a function. It actually keeps going out. It just goes out very slowly, okay? So this is a function. It goes out for the rest of time. That's why we have arrows on it. So let's talk about the domain first, okay? So the domain, let's say that this is x equals 3. If we were to draw a vertical line, it does pass through the function, okay, right there. So 3 is part of the domain. Now that's true for something like -1. -1 is part of the domain. And it turns out that it's true for every x value. If I had x equals -10, okay, somewhere over here, it would hit the graph. It would probably go through your ceiling, but it would hit the graph eventually because this keeps going, out, okay? Just slowly. So it will hit the graph. So the domain for a quadratic is actually also all real numbers. That's a -infinity to infinity. Okay. Now if we look at the range, if we were to draw horizontal lines, well, the only horizontal lines that go through the graph are the ones that start at y equals 0 and up. So anything greater than this vertex, if I were to draw a horizontal line down at the bottom over here, right? This is not, let's say that this is -4. This is not in the range. The only ones that are in the range are the ones that are greater than the vertex. So like here, at 2, we hit the graph. We hit it twice, that's fine. Remember, horizontal lines don't test for a function, only the vertical lines. So we hit this graph more than once, that's okay. But we do hit the graph. This is 2. Don't know why it's not coming out. Okay. So y equals 2 is part of the range. Anything greater than or equal to 0. 0 is on the graph, okay, right? 0 is the vertex. So our range here, I'll write it using set notation and interval notation. Our range is from 0 to positive infinity. Okay? This is where our vertex is. Okay? Or you could write it as y, but think of that such that as a but. Y has to be greater than or equal to 0. So that's our domain, our range there. Okay. Let's take one more quadratic. let's say our quadratic faces down this time. And let's say, we'll keep it simple, it's on the axis. And we'll say that this is at x equals 4. Okay. So let's look at domain and range. So once again, our domain is all real numbers. This keeps going out. It has arrows, so it continues to go out forever. So our domain is once again all real numbers. Remember, you can write it using set notation or interval notation. I don't care which one you use. I don't have a preference. Okay. Or we have, and then we have our range. So what's our range? Well, now any horizontal line that's below the vertex, because this is a parabola that faces down, any horizontal line below the vertex is going to go through the graph. So our range is anything below 4 or at 4, right? If we drew a horizontal line through 4, it's going to hit the graph exactly at the vertex. So that means that we go from negative infinity, because we're below 4, to 4. And the 4 is included. Remember, in interval notation, you put the smallest number first. So the negative infinity is smaller than the 4. Okay, so this says you go from negative infinity up to 4. You stop at 4, the 4 is included. And then if we were to do this in set notation, you would be saying it's y is less than or equal to 4 instead of greater than or equal to. Okay. Let's do one more type of graph. Let's say that we do the exponential. So again, some of you may have seen the exponential before. So the exponential graph looks like this. So it goes up even faster than a quadratic. The difference is that this, it's not a difference. It goes up much faster, but it also continues going out, okay? So once again, our domain is going to be all real numbers, because even out here, we will go through the graph. Again, it might be through your ceiling, but we will go through the graph, okay? So our domain here, once again, is all real numbers. And this time, our range, the difference is that for our range, we never actually hit 0, okay? Here, at x equals 0, at y equals 0, we do go through the graph at the vertex. Here at y equals 0, so the x-axis actually never hits the graph. This graph gets closer and closer and closer to the x-axis, but it doesn't actually touch it. So what does that mean? That means that we go from 0 to infinity, but this time the 0 is not included. And in set notation, we would be saying y such that y is greater than 0. So there's no equals to sign. Okay, we never actually touch that x-axis. Okay, so here we have domain and range. So let's take some functions, okay, and let's talk about the domain, just the domain of those functions. So in these, we're not going to be looking at graphs. We're going to be looking at the expression itself. So let's say, for example, okay, let me go back and redefine domain just to make it really clear, okay? So we said a domain of a function consists of all possible inputs. What is a possible input? The possible input is that the x value has to have a corresponding y value, and that corresponding y value needs to be real, and it needs to be defined, okay? So an x value is in the domain of a function if the corresponding y value, so the place where it meets the graph, is real and defined. And this is really important because this is what's going to help you figure out the domain of a function. Okay? So let's just do a bunch of examples. There are really only 5 possibilities here. Okay? Once we get through all 5, there's nothing else. These are the only ways that you would be finding the domain. So this is the first possibility. We have something like y equals 2x plus 3. Now, many of you are going to see this as, hey, this is a line. We know that all linear functions, if this has a slope too, it's not a slope of 0, all linear functions have a domain of all real numbers. Okay, so some of you are going to recognize that all right away. But I want you to see it the other way as well. In order for a function to be real, it cannot have a negative square root. So you're looking for 2 things in these functions. A radical. Okay. What's under the radical must be greater than or equal to 0. We call that a radicand. Right? We say greater than or equal to 0 because the square root of 0 is 0. This is the first thing that we're going to look for because this is the real part. Okay? If this were not true, then the y value wouldn't be real. The second thing that we're going to look for is a fraction. And in this one, what's in the denominator can't be 0. Because we know if we divide by 0, we get something undefined. So this is the real part. The radical is the real part. The fraction is the defined part. So in this first example, we don't see a radical and we don't see a fraction. That means that it's all real numbers. There are no restrictions. These are the restrictions. These are the buts, okay? The things that were like, okay, it could be any y value, but it can't be this, or it has to be greater than or equal to this. These are our restrictions. Since this doesn't have either a radical or a fraction, that means that the domain is all real numbers. And I'm going to switch back and forth between interval notation and set notation just so that you become familiar with both. Okay, so that's the first possibility. So you don't see any radical, you don't see any fraction, your domain is all real numbers. Let's take the next possibility. So in the next possibility, let's say I'm going to start using f of x instead of y, because remember f of x indicates that it's a function. Let's say that we have the square root of 3x minus 1. Okay, we're going to look for two things. We're going to look for a radical and a fraction. There is no fraction, so we don't have to worry about that. This will always be defined. But now we have to look at the radical. There is a radical. So that means that what's under the radical, the radicand, so 3x minus 1 is the radicand, has to be greater than or equal to 0, because otherwise you would be taking the square root of a negative number, and it wouldn't be real. So 3x minus 1 has to be greater than or equal to 0. Now we just go through and solve. Because we know what 3x minus 1 has to be, but we still don't know what has to be true about x. So we add 1 to both sides. Sorry, there shouldn't be a greater than or equal to here. This is just solving an inequality. So 3x is greater than or equal to 1. And then we just divide by 3. And we get that x is greater than or equal to 1/3. So you have to write this in interval notation or set notation. Interval notation would be we start at 1/3 and we're greater than or equal to that. So we use a bracket and we go to infinity. Okay, so in this case, interval notation is shorter to write. If you wanted to do it in set notation, it would be x such that x has to be greater than or equal to 1/3. If you plug in a number that's less than 1/3, you're going to get a number less than 0 under the radical. Okay. I'm going to do a 2a and a 2b, because we'll do two examples like this. So I'll call this a. And now let's do a b. So we'll do another one just like this. In this one, let's say f of x is equal to the square root of negative 4x plus 8. Okay, negative 4x plus 8. Well, what does this mean? Negative 4x plus 8 has to be greater than or equal to 0, right? Our radicand must be greater than or equal to 0. Once again, we don't have a fraction, so we don't have to worry about that. It's already defined. So what's under the radicand must be greater than or equal to 0. And then we just solve. Okay, this is just solving regular inequalities. Subtract 8 from both sides. That's going to give us negative 4x is greater than or equal to 8. Greater than or equal to negative 8. And then we divide both sides by negative 4. Okay, and remember, we're dividing by a negative number. So our inequality flips. X is less than or equal to 2. Okay, so what does that mean? That means our domain, it's less than or equal to 2, so we start at negative infinity, we go to 2, and it's included. Okay, or again, x such that x is less than or equal to 2. So some people prefer set notation here because then they don't have to think about what's the smallest number. Doesn't matter, whichever you prefer. Okay, so this is what happens when you have a radical. Let's talk about what happens when you have a fraction. So again, I'll do two examples. So I'll do an a and a b. And I'll put those in blue just so that you see that they're not part of the actual problem. So we have 3a. And for 3a, let's do f of x is equal to 2x plus 3 over 5x minus 15. Okay. Okay. We want to figure out the domain. Well, we look at the denominator only. The numerator, it doesn't matter, right? We could have a negative number in a numerator. We could have a 0 in a numerator. 0 over something is 0. So we have no radical here, so we don't have to worry about something that's not real. But we do have a fraction, and we said, in order for something to be defined, our fraction can't have a denominator of 0. So our requirement is 5x minus 15 can't be 0. It's not equal to 0. The 2x plus 3 is irrelevant, okay? Numerator could be anything. It's the denominator that can't be 0. So here, again, we just solved this like a regular inequality. Add 15 to both sides. We get that 5x is not equal to 15. And divide both sides by 5. And we get that x is not equal to 3. So every x value is okay except for 3. Okay, so how do we write this? So this is where people have a tendency to prefer the set notation over the interval notation. So let's talk about the interval notation. Interval notation says you could go from negative infinity all the way to infinity, but you have to jump over the 3. Here's how we do it. We say you're going from negative infinity to 3. You're not going to include the 3. And then you're going to go from 3 to infinity. And we use that or, that union here. So we have the 3 with the closed parentheses and then a 3 with an open parentheses. Think of this like you're jumping over it, okay? You jump over the 3. The parentheses are important. The 3 is not included in either of these. If you were to do this in set notation, then you would just write x such that x is not equal to 3. So you can see why some people prefer set notation here. Okay. Let's do a second one, just like this. This time, let's do f of x is equal to 7x minus 31 over 2x plus 10. Okay. So once again, there's no radical. Notice those are the two things that we always look for, a radical or a fraction. There's no radical. So the only thing that we have to worry about is whether or not it's defined. In order for it to be defined, 2x plus 10 can't be 0. We can't divide by 0. So that's a not equal to. Then we just solve it like any other inequality. Subtract 10 from both sides. 2x is not equal to negative 10. And then we just divide by 2. Whoops. And that gives us that x is not equal to negative 5. So again, in set notation, what we're doing is we're saying you're going from negative infinity to infinity, but you're jumping over negative 5. So we go from negative infinity to negative 5. Or it could be between -5 and infinity. Okay. Or we could just do our set notation. So again, you don't have to write both of these. It's just one or the other. You do have to write it in a notation. If you stopped at x not equal to -5, I would take off points. Okay? Okay, 2 more possibilities. Let's go to example number 4. Notice I say different circumstances, but what you're looking for is always the same. So the fact that there are different circumstances don't really affect you once you know what you're looking for. So the next case is, let's say we have a radical and a fraction. Okay, so we'll do an A and a B with this one as well. Let's say that we have a radical that's in the denominator of a fraction. So 2x plus 2 over square root of 3x plus 9. So now we have a radical and we have a fraction. So here's the thing. The radical says 3x plus 9 has to be greater than or equal to 0, right? This is from the radical. The denominator is telling us 3x plus 9 can't be 0, because if 3x plus 9 were 0, we would be taking the square root of 0, which is 0, okay? So our denominator can't be 0. Okay, here's the thing. You don't need to write this as 2 separate inequalities. What we're saying is this is greater than or equal to 0, but no, can't be equal to. So we're going to take out the equals. So we can combine this into one inequality where we just say 3x plus 9 has to be greater than 0. So if the denominator has a radical, then you just use a greater than, not greater than or equal to, because you have to take into account that it can't be 0 because it's in a denominator. Okay, and then you just solve it. Again, this is just solving inequalities. So we get 3x is greater than -9. Divide both sides by 3. And we get x is x is greater than -3. Okay, and that means we're going from -3 to infinity. The -3 is not included. Okay. Let's take another one just like this. Let's say f of x is equal to -5x plus 1 over the square root of 7x minus 9. Okay, so remember, from the radical, we're saying 7x minus 9 has to be greater than or equal to 0. And for the denominator, we're saying, okay, but 7x minus 9 actually can't be 0. So instead of putting in greater than or equal to, we're just going to combine these and say 7x minus 9 must be greater than 0. That's putting in the not equal simultaneously, because this has a radical and a denominator, and the radical is in the denominator. Okay, so 7x minus 9 is greater than 0. We're going to add 9 to both sides. Seven x is greater than 9. Divide both sides by 7. And x is greater than 9 over 7. Okay, and you should be becoming, this should be getting easier for you. Okay, that means that we start at 9 over 7. It's not included, so when we have the radical in the denominator, you're always using parentheses in your interval notation. We go to infinity, or x such that x is greater than 9 over 7. Okay, let's take the last example of domain. So the last example, we'll do 2 of these again, is if we have a radical in the numerator. So we have both, but this time our radical is in the numerator. So f of x is equal to square root of 2x minus 4 over x plus 3. Well, now we have it separate, right? The radical isn't in the denominator, so what's under the radical could be 0. So the radical is telling us 2x minus 4 is greater than or equal to 0. The denominator is telling us x plus 3 can't be 0. So now we have 2 separate inequalities to solve. Okay, this is the only case where we would have 2 separate inequalities. For the radical, we add 4 to both sides. We get that 2x is greater than or equal to 4. Divide both sides by 2. And we get that x is greater than or equal to 2. Okay. On the left, for the denominator, we subtract 3 from both sides. And we get that x can't be negative 3. So here's something that you need to do. Before you write your final answer, you want to check for redundancy. What we mean is x equals negative 3 already excluded in the x greater than or equal to 2? Okay, we don't want to exclude it twice. That's redundant. It would be repeating the same thing twice. It would be as if I said, Michael, leave the room, and then 2 seconds later I said, Michael, leave the room. You would feel I lost my mind. Okay, before writing the final answer, you want to make sure that the one from the denominator has not already been excluded. Did we already exclude the x value from the denominator inequality? So by saying x is greater than or equal to 2, have we already said x is not equal to negative 3? And the answer is yes. Okay. So we don't say it twice. Okay. Because of that, our answer is just x is greater than or equal to 2, or 2 to infinity. Okay, and in set notation, x such that x is greater than or equal to 2. So that's the only extra complication of having the two inequalities, is that you have to check for redundancy. If this had been x is not equal to 3, well, 3 is greater than or equal to 2, so it would not have been excluded. We'll do an example of that in the next one. I'll try and make sure that I get that. And the only difference in the set notation, and this is, again, where some of you may prefer set notation, is you would have just put comma, x not equal to 3, and then the closing brace. Okay, so let's try and take an example where it wouldn't be excluded. So square root of 5x plus 40 over 2x minus 8. I think we should be okay here. Okay. So again, we have two separate inequalities now. The radical is telling us 5x plus 40 must be greater than or equal to 0. And the denominator is telling us 2x minus 8 can't be 0. So let's go through our inequalities. We subtract 40 from both sides. We get 5x is greater than or equal to 8. I got ahead of myself. 5x is greater than or equal to negative 40. Divide both sides by 5. And we get x is greater than or equal to negative 8. This is our first restriction. Second restriction. We add 8 to both sides. We say 2x cannot equal 8. Divide both sides by 2. And we get that x can't be 4. So again, you're checking for redundancy. What does this mean? Notice we're always looking at the one that says not equal to. We're saying, has 4 already been excluded by x greater than or equal to negative 8? And the answer is no. 4 hasn't been excluded, right? 4 is greater than or equal to negative 8. So we're saying if we just use this, we would be saying 4 is okay, because it is greater than or equal to negative 8. But 4 isn't okay. So this has not been excluded. So we need to include them both, okay? So here's how we do it. We say in interval notation, we're saying we're starting at -8. -8 is included. And again, we have to jump over the 4, right? So we go to 4, we close it, and then we open it. This is a jump over. And we go all the way to infinity. So that's how we would write it in interval notation. In set notation, it would just be x such that x is greater than or equal to -8, comma, x not equal to 4. And now you can see why a lot of people prefer set notation. Okay, so let's just do a couple of examples with checking for redundancy, just so that you get the hang of it. And then we'll be done with this one. So let's say that we had x is less than or equal to 3 and x not equal to -2. Okay. Has this already been excluded? Well, we're looking at this and we're saying -2 is less than or equal to 3. So that would be saying that -2 is okay. Okay. So we need to include both because -2 is not okay. -2 is less than or equal to 3. Let's say that we had x greater than -6 and x not equal to -5. Okay. Actually, I'm going to change this to -7. Okay, x not equal to -7. Okay, so the question is it redundant? Is -7 greater than -6? No. Okay, that means it's already been excluded. Okay. -7 is not greater than -6. Okay. And just here, just for the interval notation, in the interval notation for the first one, we have to include both. So if we include both, what we're saying is we're going from -infinity, because we're less than 3, to -2. Then we jump over the -2, and we could go up to 3. So keep in mind, when you're thinking about this, my suggestion would be draw a number line, pick out the -2, pick out the 3, and just draw your circle there. You're going from left to right. Okay, so -infinity to -2, jump over the -2, stop at the 3. Okay, that just might help you with the interval notation because we go left to right. Okay, this one is easier because there's only one of them. Let's do one more. Let's do x is greater than or equal to 5, and x is not equal to 8. So again, we're asking about redundancy. We're saying, have they both been included? Okay, I'm just going to leave this here because I can't seem to erase it. So here, we're asking ourselves, has 8 been eliminated? So we need to include both because If we put 8 in here, 8 is greater than or equal to 5. Okay. So what that means is, let's just take a look at the interval notation. Remember, in set notation, you would just write x greater than or equal to 5, comma, x not equal to 8. Here, this is saying we're starting at 5. 5 is the smaller number, right? On the number line, 5 comes before 8. So we start at 5. It's included. We keep going to the right until we reach 8. We jump over the 8. And then we just keep going to infinity. Okay, and that's it. So this is still main. Okay, 5 different things. Radical in the numerator, radical in the denominator, only a denominator, no radical, only a radical, no denominator, or no radical and no denominator, which is the only case where the domain is all real numbers. That's it.